Hello guys, this is group number 3. We're going to introduce you about aldehydes and ketones functional groups. So let's get started. Ketones and aldehydes, both of them contain a carbonyl group, which is a carbon bonded with a double bond oxygen, as you can see over here on the picture. So the major difference between both of them is that aldehydes contain an R group on one side and it has a hydrogen atom on the other side. And for ketones, on both sides, that one contains a alkyl group or R group. The geometry of aldehydes and ketones, it's basically a triangular planar. As you can see over here in this picture, both of them are the same. The main difference is one has H on it, and the angle approximately on both of them it's 120 degrees, as we can see on this picture. The hybridization in aldehydes and ketones, it's a sp2 hybridization. So the carbon, two of the sp hybrid orbitals in carbon, which is on the carbonyl group, are gonna form sigma bond, one with the R group and the other one with the hydrogen group on the aldehyde. For ketone, it's gonna form one on the R group and the other one on the R group. So the remaining sp hybrid orbital, it's gonna be bond with the oxygen atom, and the unhybridized p orbital on the carbon, it's gonna be overlapped with the oxygen, forming a pi bond, which we can see on a double bond. The properties of aldehydes and ketones. So both of them exhibit dipole-dipole interaction because their polarity of the carbonyl group. They don't have oxygen and hydrogen bonded, so two molecules of aldehydes and ketones are incapable of intermolecular hydrogen bond, making them less polar than alcohols. So the solubility of aldehydes and ketones, well, both of them are soluble in water, but their solubility decrease as they decrease on length in the chain. So we will see on the next image. So over here we can see some of the properties of aldehydes and ketones. We can see boiling point as they increase exchange and intermolecular forces. They increase in boiling point too. The solubility over here, it says that both of them are soluble regardless the size. So aldehydes and ketones with less carbons are soluble in water, but if they have more than 5 carbons, they become insoluble because nonpolar alkyl portion is too large to dissolve in polar water solvent. How do we name those the aldehyde group? So let's get started. The aldehyde, it's always bonded with either a carbon chain or a ring. So in this case, let's start with the carbon chain. So the carbon chain, we have to find for the largest chain. So here we see it has 4 carbons. It's 1, 2, 3, and 4. So it's butane. But we have to change this E over here for the suffix AL. So it's going to be a butanol. The next step is see if there's any substituents on the chain, and number them and give them a name. So over here we see it's a substituent number 2 and number 3, so which is a methyl butanol. So the name on this one is going to be 2 and 3 dimethyl, because we have two methyl groups. So it's going to be 2 and 3 dimethyl butanol. So this is the name for this one. Let's see, for the rings. In the if aldehyde group it's bonded with a ring, we have to name. We have to see how many carbons are on the ring. So in this case, it's a cyclohexane. So we can see it's a 6-carbon ring. And also we have to add carbohydrate at the end. So this is the carbon, the aldehyde group. So we have to name it as 1 always in the ring. So it's gonna be 1, 2, 3, 4, 5, and 6. We have to call the substituents, name the substituents. So on this case, we have a ethyl group over here on carbon 2. So it's gonna be 2-ethyl cyclohexane carbohydrate at the end. Okay. So this is most common names of aldehydes is formed by taking the parent common name and adding this adding the suffix aldehyde. So this table we can find it on the book, or we will see in here. It's both, all of them are aldehydes. So but they differ on this side, or basically on the chain that they contain. So for example, it has this first structure, it's called form. The partner name is form, so the name is gonna be formaldehyde. And for the second structure, it's a acid. This side, it doesn't have a hydrogen here. It's a R group, so it's gonna be a acetaldehyde. Acetaldehyde. And for that one, we see it's 1, 2, 3, 2 more carbons, so it's gonna be a propionaldehyde. And we see as it's increasing 1, 2, 3, 4, so it's gonna be a butyraldehyde. And one more time, it has 5 carbons, so it's gonna be a valeraldehyde. And so on. So we have, I think we have to memorize this table. Don't forget to study it on the exam. So let's see an example here. Let's call this aldehyde. So we see it's an aldehyde over here. It's a H hydrogen atom over here, but it is invisible. So we just know that this is an aldehyde. It has an R, so that means it's a ketone, but we will see and figure out this one first. Okay, on this one we have to name all the chains. So we have 1, 2, 3 chains, and we have one substituent, which is a chlorine atom. So we will call 2-chloropropanol. We have a propene over here, so we have to change it the N with the L. So it's going to be a 2-chloropropanol.
1. Find the longest chain. In this case, the chain contains 8 carbons or an octane. Change the ane ending to an ol. 2. Carbon 1 should contain the aldehyde functional group. 3. Identify and name the substituents first. In this case, it's 2,6 and 6-trimethyl. The answer is 2,6,6-trimethyl-octanol. 1. Find the name of the ring. In this case, it is a cyclobutane, and add the suffix carbonyl aldehyde. 2. Carbon 1 should contain the aldehyde functional group. 3. Identify and name the substituents first. In this case, it's 3,3-dichloro. The answer for this is 3,3-dichlorobutane carbondialdehyde. 1. Find the longest chain. In this case, it contains 5 carbons, or a pentane. Change the ane ending to an ol. 2. Carbon 1 should contain the aldehyde functional group. 3. Identify and name the substituents first, if there are any. 4. The answer for this is pentanol. Naming ketones and the IUPAC system. 1. If the ketone is bounded to the A carbon chain, first find the longest chain that contains the ketone group. Change the E from the alkane parent and add the suffix "-one". 2. Enumerate the carbon chain and add the lowest number to the carbonyl group. 3. If there are any substituents on the chain, number and name the substituents. 1. Number the chain or ring to put the carbonyl group at carbon 1. This number should be omitted from the name. 2. If there are any substituents on the chain, numerate them after the ketone group. Common names of the ketones are both formed by the alkane group on the carbonyl group. Arranging them alphabetically and add the word ketone, like on this next example. Acyl-methyl ketone. Examples of ketones. 1. Find the longest chain containing the ketone group. In this case, it contains 7 carbons, or an heptane. Change the ane ending to an -one. 2. Numerate the carbon chain. Give the carbonyl group the lowest number. 3. Identify and name the substituents and add, in this case, 3-acyl-6-methyl. The answer to this is 3-acyl-6-methyl-heptanol. 1. Find the longest chain containing the ketone group. In this case, it contains 7 carbons, or an heptane. Change the ane ending to an -one. 2. Numerate the carbon chain, giving the carbonyl group the lowest number. 3. Identify and name the substituents and add, in this case, 5-acyl. In this case, the answer is 5-4-octane. 1. Find the longest chain containing the ketone group. In this case, it contains 7 carbons, or an heptane. Change the ane ending to an -one. 2. Numerate the carbon chain and give the carbonyl group the lower number. 3. Identify and name the substituents and add them first if there are any substituents. In this case, it is just 3-octane. 1. Number the chain or ring to put the carbonyl group at carbon 1. This should be omitted from the name, so it is a cyclopentane. Change the ane ending to an -one. 2. If there are any substituents on the carbon chain, numerate them after the ketone group. In this case, the substituent is 3-acyl. The answer to this is 3-acyl cyclopentane, unknown. Here are some practice problems. Try to do them at home. Here are the answer keys. Source: Smith's J.G. 2008, Organic History, Boston, McGraw-Hill.